Right, so welcome back to another lecture, which is we're talking about something very really appropriate for these days. Uh, this is kind of a pandemic, but it is not in that stage. But it's the same virus group, which is corona. Um, the first one, which is outbreak, in 2002, we call it SARS, right? And we're going to look at how to model something like that. Maybe this is useful for what you do out there, right? And we're going to look at how to model this using our little tools and what are the things we have to consider when we're doing this. Okay, right. So let's get started. What is SARS, right? Well, the SARS is we call that a severe acute repository syndrome. So that's what SARS is, right? So uh, and this came out in the first case occurred in 2002 November, and then they were published that in 2003 actually. Uh, by April 2003, it's reported the cases 2000, yeah, and then by July there were 800 deaths and 8,400 more cases. So, but one thing that you may notice here is the death rate is a bit higher than the COVID-19. Um, so I think this is the first wave of corona group that outbreak, and then the second one is MERS, I believe, as I recall. MERS is called Middle East uh, repository syndrome. So that's the second one. And the third one is the COVID 19, which is going on right now. So the differences between those, the COVID 19 is very contagious and it is spreading like wildfire. And but the death rates are less. Okay, so that is the difference. But you can see even uh, that what we had before. Uh, if you're looking at the effect on this virus group, especially it's hard hit only China, Canada, and Hong Kong, uh, and those countries. I think the Canada is the only one which just came up to the American continent by then. Uh, I mean the hard hit the areas. If you get the Canada here, right, that is one. And but whatever it is, the impact of that is very important, right? So the unemployment rate, you can see here the unemployment rate raised up to this by only this much impact, right? So there's the total cases, and of course the Canada, the, the the cost per day is this much, right? Okay, it's 30 million estimated cost per day due to this issue, right? But imagine now we have a huge impact by the COVID 19. So it might be, if you're thinking of economic impact on that, that will be a heavy magnitude than this, right? So, yeah, here in this book they discuss about this part and saying, okay, it's affected this much, but I think this is right now it's a 40 or 50 times bigger impact happened by the COVID-19. So I've just assumed this number. There's no there's no legitimate data to assume it is 50%, 50 times more impact. Maybe more. It is still going, so it can be more impact on the economic tides between countries and all that, right? Okay, so especially because of this restricting the international traveling and the trade and all that, so the business are not going to be as well as it has to be, and also the how it's impact each individual, right? Okay, that's the introduction. What is SARS is? SARS has the same kind of symptoms. That's why they call it, all three are the same corona group, the viruses, right? And I mean the corona group virus, and then has three names. One is SARS, the other is MERS, and the other is COVID-19, right? So the one very recently, I mean currently affecting the world, right? Okay. So when you're looking at this, how are we really going to group the people? Uh, how are we going to the group the people in order to analyze this or the model this, right? So this is the simplest way that we are going to take over this, right? And the note is that when you're modeling this, we consider closed environment. So that means what? Well, these are the assumptions that you're going to make, right? So the assumption is we're going to look at the closed environment, and there are no births, deaths, and immigration and emigration. So what is the difference in immigration and emigration? That means the people not coming into the contained environment, nobody going out. So there it is, a fixed closed environment. So those are the assumptions. So it is actually we just looking at the basic uh, the model here, right? It is not going to be much more realistic, but it's a good start. So then you can apply all these constraints later on and see how that behave when you really having everything else as well. Okay, right. So for now we will stick with these assumptions. So those are the assumptions. So very important, if I ask you to do something using this in the exam, you should know what are the assumptions on this model. So understanding is very important on that, right? Okay, so then we divide the people into three groups. The one is susceptible, right? Has no immunity from the disease. So whoever gets caught with this one, you get sick, right? So that means if the virus come to these people, they get sick. So the sick people, we call it infected, right? So these are the infected. So we have people who are not sick, happy, right? And so they are dancing, right? So no sick at all. And then infected are the sick people. So we will have, they're on the bed, right? Well, they have they got infected, right? Right. So this is group number two, which is the sick ones, right? So these are susceptibles, right? It's not sick, and infected are sick, right? And then you will have uh, recovereds, right? Okay, so the recovereds won't sick again. So they assume they have enough immunity, so they won't get sick again, right? So these are the recovereds. A little bit happy, right? So after they get sick, they are recovered, right? Usually, in cases of viruses, uh, it's really unlikely that you get sick again, but it is not ruled out like that. But most cases, they will build their own mechanism to defeat this virus after you get recovered. So that is what the flu shot is all about. Flu shot is building immunity for those kind of things. So they inject actually the mild way of the diseases to you and build the immunity inside you. So then whenever it's get hit by any virus, you won't get sick. So that is what the what is the purpose of you taking vaccine, uh, season vaccines that you're going to take. Uh, that is the purpose of it. Okay, so just to build the immune system. Right, so your body eventually going to create something. All right, so these are the three the groups that we are going to talk about, right? One is the susceptible group, and they can get sick when they contact with these guys right here, right? So these two are whenever they get together, well, these guys become these people right here, right? If you are become sick, that is the only way out is this. So yeah, there can be some people who are falling into recovered groups but never got infected, right? So that means they have immunity system by their system, whatever they did before or something like that. They are really immune, right? So that can happen too, right? So in that case, they won't get sick very easily. But here we going to get this closed environment, right here, and we divide the people in there into three groups. One is not sick but very uh, they may get sick, right? The other ones are already sick and the others are recovered. Okay, so those are three groups that we can divide these two. The susceptibles are the ones who are vulnerable to get sick. Okay, all right. So let's move on. And so the differential equation. We have three things to consider here. We're looking at the first one, which is right here, the recovered rate, right? So recovered rate, so for you to get recover, of course you have to be infected, so that's what it means here, right? Right here it says we say the recovered rate is proportional to the infected, right? So you have to be infected, of course, to be recovered, so that's what it means. And also so what are these D and DT means? Let me recall what it means, right? If you forget what is calculus means all about. So this is delta recovered over delta time, right? So what does that means is if you draw a graph of the people who get recovered is here and over time is here. So if I draw a graph like this, right, and by the time how many got killed, so that's what it is, and then instead of you calculating all the people total like this, you can break it to little pieces, right, like this, right? I can divide it to little pieces and see each one. You can calculate each one very accurately. So in that case, you can calculate the whole thing. So that is the idea of if you have a graph like this, how many total recovered, you can calculate it by just adding little pieces, right? So that is the idea of calculus. So how do I do that? Well, I just divide it to smaller pieces. So this is the small piece of R over a small piece of T. So that means the recovered rate. So this is the same thing that we write as dr by dt. So it's the rate between small piece of this, and then you can add all together and come up with a big value. So it says okay, so this is already proportional, directly proportional to the infected, the number of infected, right? So that's what it says here. And then to get rid of this proportional mark, of course I had to apply or introduce a constant. So this constant is called the proportionality constant, right? So how do I come up with a proportional constant in this case, right? Well, that is what we explain the next line right here, okay? And the only thing that you have to make sure, keep in mind, this d right here has nothing to do with this d right here, okay? These are not equal. These are two different concepts, okay? Right, so I know some people get confused when you're having a dd like that, right? So that's why I just mentioned that. But anyway, so the let d is the number of days that someone remains infected. So if you have the days of somebody infected, so then the a will be 1 over d. So that's what it is, right? So right here, this is what the constant is, right? So there's an example here. If a boy usually sick with the flu for 2 days, then the d is 2, and the a is going to be 1 over 2, which is equal to 0.5. So this is what a is, right? Okay, so that's what it is. So yeah, so now we know how to come up with the rate of recoveries, right? Rate of recoveries actually is equal to 1 over number of days, right? 1 over number of days multiplied by infected. So that's what it is, right? So this is the constant we call a, okay? Right, so that is for the recovered. So let's move on. So now we have two more to figure out. One is the rate of so we know the recovered rates, and we have to find how many get infected, right? And so that means how many will change from susceptibles to the infected. So the change of susceptibles, that is what we're going to look next, right? Before that, let me point out one thing here, very important, which is how we really going to get infected. Okay, so this is where we're going to analyze this issue of change of rating. I mean the change of rate on susceptibles. Okay, right. So this is a good example here. Assume that there are two people who get really sick. So this is one person, and this is the other person, right? So there are two people are sick, and these people right here are not sick, right? But unfortunately, when they get contact with these two, right, right here, so how many ways that this connection can happen, right? Okay, so the Andre here can have a connection with Joe, Lee, and Orlando, and also Leslie has the same probability of go and connect to the other people. In that case, the total possibilities that we have is 1, 2, 1, 2, 3 blues, and 4, 5, and 6, right? So there are 6 ways to be we can make the combinations or possibilities. So the total possibilities is nothing but this, how you calculate this is you multiply the infecteds and you multiply them by the number of the susceptibles. So in this case, that is nothing but S multiplied by I, right? So this is what you have right here. So the total possibility of interactions is 6. Right, so this is something really important, especially today. What is the COVID-19 is causing is through the interactions, right? Mostly through the interactions. So if you get sick and if you go to other people and if you have possible connections, of course, that gives you more impact. So like that, it will spreading more and more through these kind of situation, right? So uh, this is the main cause for diseases to spread, right? The only one problem in COVID-19 is you don't see the symptoms the right whenever you get infected. So you don't know, you still feel healthy and all, then you go and contact with the other people. Eventually the virus will spread, and but you are not sick or the other one is not sick until few days later the both are going to get sick. So in that case nobody knows. So that's the bad part. That's how that causing this much trouble. Okay, right. Okay, so then let's move on to the next one, which is how we're really going to calculate the, uh, the susceptible rate of change. Okay, so how we going to calculate the change of rate for susceptible? So this is what we're going to look at now. Okay, and so you can say obviously that we saw the combination of two groups. Right here it shows when you're having A and B groups. This is A right here and this is B right here, and you can make all the combinations out of that, like we saw in the last slide, and you multiply by a constant. That is something that we can come up with for the rate. So the ds by dt, which is susceptible change of rate, we can say this equal to negative constant time si, right? Oops, let's jump to the next slide. Right, I'm coming back. Okay, so what is this negative? Why is it negative? Well, the reason for you to have a negative value is if you have one group here, which is who are not infected, the others are infected, right? So changing people from here to here, so that's where it's jumping, right? That's the change rate. So that means infecteds are increasing, susceptibles are decreasing. So this rate will actually causing this amount, which is the S amount, to be decreased. So that's why you have a negative value right here. Okay, so that's the reason that the change rate for susceptibles are negative. Okay, and all right, so this is nothing but the number of susceptibles right here, and number of infected right here. So that is the multiplication of the product of those two. So then R, what is this R? How do we calculate the R? So this is the next question that we have. How are we going to calculate this one right here? So that's what explaining on the next few lines here. Well, we have to consider the probability is the one part of this, is how to calculate the probability. What is probability? Well, probability is, let's say now for example on this particular example, if you get environment, right? Environment, this is the environment. We have three groups here, and some were sick, some were not sick, and the others are recovered, right? So you call this total number of people n here, right? If you get that, so the probability of the people in here are not infected, who are susceptible group, is the probability of the number of having here, we usually call out of total number this many is not infected. So this is what the probability means, right? Out of total number, how much it is. So this is what it means by probability. So probability of susceptibles, right? So that's what it is, S over N. And okay, so we're going to break that to more. Here it is, let K be an infected contact per day, and the probability that this is spread during such contact. We call it B. So, so the probability that disease is spread during a contact is B, and the K is an infected contact, right? So that means if some person is sick, how many contacts that he going to make per day and get people sick. So that's what K is. So in this case, we define uh, the product of those two is KB, right? KB, and we divide that by N is what we call R, right? Okay, so this is what R is all about. So we'll analyze this a little bit more on the next slide. What does this actually means, right? And how we really going to calculate that by the given details, right? So that's what we're going to look at next one. All right, so this is where the examples comes in, right? So suppose the average infected child has 33 contacts per day. So how do I know that? How much contacts? What does it mean by 33.3? There's no points, right? Well, uh, you cannot say 33.3. This 0.3 is not a person in that case, right? So it has to be a whole number. But anyway, what this means is what we showing on this down down here. So we'll come to that in a minute, right? The first, let's say, what does this means? How do you calculate this? So the child had 33.3 contacts per day, and the probability that contact result in spread of disease is 5%, right? So if you have 100 people, well, by contacting, you get 5 of them sick. So that's what it means, okay? If you have total 100 people, 5 get sick by this many contacts, right? So that is the average contacts. So that means, right, so this person, whoever it is, so this is a susceptible group right here, right? And so you have some number of people here, right? And so there's another person goes in, which is I, right? And he get interact with these people right here. So this is the interaction, okay? And this interaction make them sick, but not all the people who are interacted get sick at once, right? So that's what it means. So that means, okay, so even I have 33 per day contacts with this I guy, right? 33 0.3 per day contacts with this I guy and the S. Still I get sick only 5% of them, right? So what this means is, okay, if you have 100 people, right? 100 people, only 33, I mean only 5 people get sick out of that. So that's what it means, okay? And yeah, so if it is one person, right? If it is one person, that means 5 over 100 get sick, right? So if it is 33.3 people, so that means you multiply by this by 33.3 get sick. That's what it means, okay, out of this total. But here, okay, so this is actually we call this which is the per day, how many people get sick, and that illustrate as a, and K is, what is K here? So it is the next question, right? What is K? So the K is this one, which is the contacts per day, right? Contacts per day is this, right? and how many get sick by this contact is your B, which is this one right here, right? Okay, so then what is the probability of this? I mean, how do you calculate the transmission constant? Is you get these two values and you divide it by the total population, right? So in this case, this is actually equal to the K is 33.3 multiplied by, right, uh, 0.05, right, which is this one right here, and you divide this by the total population, which is in this case is 763. So this will give you something like 0.0028218, right? So that's what it says. Okay, so this is how we calculate that. And what does this means by this? How do you calculate how many get sick per day, right? And it is giving you a fraction here. So what does that means is if you say if 80% of the susceptible people get sick in flow and remain for 3 weeks, right? So you can calculate this one obviously, right? So you can say, okay, if you take 100 people and out of 100, 8 people got sick within 3 weeks, right? So that's what it means. So that means out of 100, 80 of them get sick within 3 weeks. So that means how many people get sick per day? Well, you can say 80 divided by 21 out of 100 will get sick per day. So that's how we calculate the per day rate, which is the K value right here, right? So that's how we calculate that. So where the K comes in? Well, the statistics, you have to collect the statistics for this. So that means day 1 how much, day 2, day 3, and so on. You take all the days and then you see how many total, and then you divide that total by the number of days, right? And then you can come up with average sick per day, right? So that's what it is. Okay, yeah, you don't have to worry about this part right here. This is not related to that. I'm just showing you how to calculate that for the total population. This many people per day that get sick. So actually, yeah. So this is what the total number of people get sick per day. This is what is actually we got here, right? Okay. So yeah, what I'm saying is this part right here is not in the book. I just calculate just to show you how you calculate that and apply, right? So this is this many people per day. If you get the total people, but this is the way it's calculated, that one. Okay, all right. So let's move on. So this now you know how to calculate ds by dt, right? And this is equal to minus r, right? S and I, right? Okay, so what is minus r? So the r is nothing but this value right here, right? And the kb over n, so this is what r is. Okay, right. So now we know already two things, right? So we have a group of a group of three in our whole container. One is we already know who are susceptibles, and the other ones are infected people, and then we know recovered people, right? If you know two of them, obviously the other group will be we can calculate the other group by difference of these two. So that's what it shows here. And this is the equation they came up with, right? So this is what is it means is what I gains come from S, right? So the S when whatever the I gains and S lost, right? So what I mean is this is something like this, and then you give it to the I here, right? And then from here, which is what R gets, right? So this is how it moves, okay? And so at the beginning, whatever this lost, S lost, I gets, I lost, R gets. So that is what saying here, right here, right? I losses, R acquires, okay? So the differential equation for the rate of change of number of infecteds is a sum of the negatives of all two rates, okay? So this is what you come up with for uh, the rate of infecteds, right? Okay. So the other way that you can write this as we already know what this is. We already know what this is, right? We know the equations for these two, right? So that is what we wrote here, right? So since this is a negative value, and then already we have uh, the ds by dt, right, is equal to negative r a r s and I, right? So when you apply this one with the negative value here, right, eventually you'll get uh, eventually you get positive value right here, right? So that's the positive value you have, okay? So by saying that, so you'll have uh, di by dt is equal to rate of susceptibles uh, minus change of recovered. So that's what they come up with, okay? So if you calculate recovered, if you calculate susceptibles, you can easily find the rate of uh, change rate for the I by just having addition, negation of the additions. What I mean is negation of the additions means you have this dt plus dr over dt, and you can take this minus right here. So that is negation of sum of these two. That is equal to this value right here, okay? And of course you can apply the, the right hand side of those two equations we discussed before, right? So so up to now we calculate what, now we know what is ds by dt, we already know that, and we know what is di by dt, right? And then the other group dr by dt. So we know all three. Now we're good. So we know all three, so we can put those values in the rate of changes and then see how our Vensim simulation is going to work, right? So that's what we're going to look at next. And here it is, right? Well, you have to have the initial values, of course. Susceptibles are the community that is not sick, and the transmission constant, like the examples that I just showed you, you have that value here, uh, right here, right? And then the getting sick is the transmission constant. So this is how you calculate how many people get sick, right? And that means and then that is equal to the transmission constant multiplied by susceptibles and then infecteds, right? So these are the interaction of these two with a constant value will give you how many get sick. And well, initially we consider infecteds are zeros, and the recovery rate is a constant value. We put it zero point 0.5 there, and the recovery rates with multiplied by infected. So this is AI, if you remember, and recovers at the beginning is 0, right? So if you put all these equations together, this is the Venn diagram actually. So we have the initial value for this one right here, which is 762 at the beginning, right? When the time is 0, when the time is 0, this is 762, and I got 1 sick, and I have 0 here. So that's what the initial values, and the rate of this, right? You can calculate the get sick, the transmission rate, and we have already calculated that to equal to 0.0028 to 18, and the recovery rate we have 1 over 2 days, which is equal to 0.5, right? So that's what we did in our example. And okay, so we know the rates, right? So the getting sick is we calculate that one already, and the recovery we calculate that already. And then what we gonna do? So we're gonna simulate this, right? So when you simulate that, uh, uh, this is what you get, right? So you can see there's a break even right here at this point, and then the infected is going up like this and going down like this. So this is the curve. Actually, you may see this in the COVID-19 in the when you're looking at the Chinese uh, already who conquered this one, right? So they have uh, it is like this right now, and then you're flattening the curve means you stop increasing that, and you are trying to make it come down like that, so it's more recovered, and when you're reducing the amount of increment of these infections, right? So anyway, so this is a very basic simple way of modeling this with some assumptions. Of course, we have few assumptions: no deaths, no births, nobody goes out, nobody comes in. So it's a lockdown city kind of situation. That is, nobody goes out, nobody comes in, and you don't consider the natural deaths and the births. You consider only the sick people and this, because you keep your constant population intact. But that is not the reality for the COVID-19, obviously, or the SARS. There are people die from it, right? So then you have to apply that constraints if you want to get an accurate model, right? But so this will predict things, and it will tell you what happens when the time phi, right? So these are the weeks, I guess, here, and then the population, what happened to the population. So eventually, well, the susceptibles, there are more right here. So that means did not get caught with, this part right here, the still susceptibles are there, who did not get caught with the flu, right? But well, most of the people from here to here it came down, means a lot of people got sick, right? And then the recovery is going here. So there's a difference between these two at the end. If the infected goes to 0, means this different, means those are the people who did not get sick. If this blue line is 0, that means at that moment the range between these two is are the people who are not get sick. At the end, there will be recovered and susceptibles, right? No infected. Right. So this is pretty interesting uh, way of modeling things, right? So what I'm expecting you to understand here is, yes, the rates of how you come up with the rates of ds by dt, right? That is one thing, right? and the di by dt, right? And then also, how do you come up with dr by dt, which is the easiest one out of all, right? So how do you come up with the constant value? How do you come up with these values? That is all I'm expecting you to understand, right? Okay, so if you know those things, uh, you're good to go with it, and you don't have to worry about much more the things that I did not cover here. There is more things they're talking about in the chapter. I will point out one which is pretty interesting, about how you apply the quarantine into this, right? If you did that, uh, actually the quarantine part, we could have control COVID-19 up to some extent. So that is, quarantine is very important. So this is one thing people would do. Some countries would do. I know the Singapore did a lot of work. Like, for example, if they find one person who is infected, and then he traces how many people he contacted, and where he went and all that. Maybe it's and then calculate all the possibilities the others get infected. So then they were following them carefully. So it will go 3 levels down, I think, to control this. So that's how they came up with a good schema. So whenever they find that people who are contacted, they put them in the quarantine, and the quarantine will under process like that. So they keep things under control, especially in Sri Lanka. They do that. It's pretty good. So they come to the top 5 countries who's taking care of this pandemic so very seriously, and control it very effectively, right? Yeah, you can see now, if you don't get control like that, how fast it spreads, right? And it's getting out of control. The only problem here is, well, the COVID-19. Of course, you need the breathing support when you get sick, right? So that's how you have to, if you want to get survive with that. Maybe most of the people, they need the breathing support, right? So, but the problem here is the number of get sick at a time. So this is a time issue actually. The problem is the time and the available resources by the given time. So if you have more sick people who need oxygen, and if you don't have enough resources to provide that, that is the chaos starting, right? So yeah, that's why it's important to keep it under control. uh, Take time, right? That is one way of doing it. Like, yeah, it's spreading, but still take time. Don't let it spread fast. So the rate, we have to change the rate of infection, getting infected, right? So that's what one of the things I found in this chapter is pretty interesting, is how you going to control that, right? So this is one of the charts that they're giving. The susceptibles are here. You eventually, anyway, you're going to quarantine them and check uh, whether you're good or not, right? So and then so if you have exposure, so then again, like for example, I said, if there's a sick person contacted you, but you're not sure whether you're sick or not, right? um, so then you can put into the quarantine here, right? So this is what it is, says susceptibles to expose quarantine. So that's what it is. And then so then in this quarantine you will find he's infected, so it will go to infected quarantine. exposed to quarantine into infected quarantine. So that means this one right here. And so that process is going. Either this person is going to be uh, uh, the record, or or die. So this is what quarantine to death. So eventually that is the end of it. So that's called SARS death, right? Or if it is not, this is isolated quarantine. So that means he will be locked down. I mean, he will be in a lockdown area. So that means only doctors can go and check him, not the other outsiders, right? So that is infections isolated. So anyway, if a susceptible has no quarantine and they're going to exposure, and this is the path of that is going. So um, yeah, go through this and see how many connections, how many ways that you can prevent this going uh, to slow down the rate. So that is the most important thing here, right? Right now, until you find a vaccine or anything on this kind of a pandemic diseases, the best thing you can do is follow some quarantine process to slow it down. So if you slow it down, of course, you have enough resources to support them. Uh, if you don't have enough resources to support them while they are sick, that is where the problem actually that you have to address. That's how the death rates going increases. It is it is eventually it is kind of a flu kind of a thing, and so the following these quarantine steps is very important to control something which is going beyond beyond our control for some extended of time, right? So yeah, so I will stop here, and we'll talk about malaria on the next one, and how we're going to actually take care of model something like malaria. uh, so we'll look at that in the next lecture. Okay, right? So right, see you on another lecture.